Hello, it's Stat135, Lecture 14. Last time we started section 9.2 on the Neyman-Pearson paradigm, which is a frequentist way of doing hypothesis testing. We discussed type 1 error and type 2 error. Type 1 error is the probability under the null distribution that you reject the null. And type 2 error is the probability under the alternative distribution that you accept the null. If you have a simple hypothesis, such as that the null, when you flip a p coin 3 times, that the null is that p is 0.5 and the alternative is that p is 0.7, that's called a simple hypothesis because the alternative and the null are single value. We saw last time that we can write out the likelihood ratio, which is the ratio of the null density to the alternative density, and what we see is that when the likelihood is large, we want to when the likelihood is large, we want to accept the null, and when the likelihood is small, we want to reject the null, right? So when the likelihood is large, that means that F0 is large and F1 is small, and F0 favors the null. So the likelihood ratio always has the form that we reject the null if the likelihood ratio is less than some constant c that's determined by alpha. So today we're going to look at the power of a test and how to find the rejection region of the likelihood ratio and how to find a p-value. So section 9.2, power of a test. So power is 1 minus your type 2 error, or 1 minus the probability under the alternative hypothesis that you accept the null, which is the same as the probability under the alternative hypothesis that you reject the null. And in the previous example, the power, which is the probability under the alternative that lambda is less than 1.94, we would read the F1x column here for when lambda is less than 1.984, which is 0.343 and 0.411. And that is 0.784, that's the power. So you want power to be large because power is 1 minus type 2 error. So finding the rejection region and power of the likelihood ratio test is the next topic. So let's take a look at an example where under the null hypothesis, x is uniform 0, 1, and under the alternative hypothesis, x has density 2x. So we're going to look between, I should have said here, x is between 0 and 1. So what is the likelihood ratio for alpha is 0.1 level of significance? What's the power of the test? So you should just be able to actually figure these things out from the picture without doing any calculations. You can see here that you would want to reject to the right of some point. It turns out to be 0.9, but you can tell it's going to be to the right because to the right of some point, h1 is above h0. So we're going to reject to the right, and under the null distribution, if alpha is 0.1, that would indicate that the area under the null is 0.1, and because the null distribution is just uniform, that would mean that the width of our rectangle here would have to be 0.1. So hence the cutoff is going to be x is 0.9. But so the rejection region is 0.9 to 1. But we can actually calculate it explicitly if you want. So you're just solving for c here, and so 0.1 is the probability under the null that x is greater than 1 over 2c, which amounts to c being 1 over 1.8, or equivalently x is greater than 0.9. To calculate the power, that is the area under the alternative hypothesis above the rejection region. So that's what's shown in blue here. And we don't need calculus, but we can just solve this as an integral as well. So it's the integral from 0.9 to 1, because that's the rejection region, of our density 2x, which turns out to be 0.19. Okay, so why is the likelihood ratio test any good? So in fact, for simple hypotheses, it's the best you can do. It's the most powerful test that you can have. And that's what the Neiman-Pearson lemma says. We don't need to look beyond the likelihood ratio test if we have simple hypotheses. Unfortunately, most hypotheses aren't simple. So when we are looking at at more complicated hypotheses, we'll have to investigate this further, and that's coming next time. So now we're going to talk about p-values. So a test statistic p-value is the probability it's as or more extreme than what you observe. So the p-value is the area under the null distribution. In this case, if your rejection region is to the right, it's the area under the null distribution to the right of your test statistic. And you can compare that with alpha, which is the area to the right of your the area to the right of the cutoff point, which corresponds to the entire rejection region under the normal distribution, under the null distribution. Excuse me. So you reject the null if the p-value is less than alpha, since in this case the test statistic is in the rejection region. Let's just take a look at an example here. So say that x is normal mu 25 squared. So our null is that mu is 100, and our alternative is that mu is 125. So then the likelihood ratio test says reject the null if x is greater than 125, and you observe 100. So let's find alpha. Okay, so alpha is the area under our alpha is the area under the null distribution to the right of 125, which is your rejection region. Okay, so that's 1 minus phi, 125 minus 100 over 25. And just to point out that power is under the rejection region, above the rejection region under the alternative distribution, that area. So that's what's shown in red here. And the p-value is what's shown in blue, so that is the area to the right of 100 under the null distribution. So that would be 0.5. So the p-value is greater than alpha. The p-value is clearly greater than alpha here. You can see from the picture, so we would accept the null. So suppose that test statistic has the standard normal distribution. If the test rejects for large values of the absolute value of t, what's the p-value if you observe minus 1.5? Okay, so I've drawn the distribution for t. It's standard normal. Okay, and if t is minus 1.5, then the absolute value of t is 1.5. And saying that we're going to reject for large values of the absolute value of t means that we're rejecting when the absolute value of t is large, and the p-value will be under the null distribution here. So it's the probability that the absolute value of t is greater than the absolute value of minus 1.5. Now I'm taking the absolute value of 1.5 because t is, in this case, minus 1.5. That's our observed value. And so the absolute value of t then is the absolute value of minus 1.5, which is 1.5. So this is equivalent to saying that it's the area to the left of minus 1.5 or to the right of 1.5. So that's 0.1336. And just note that if the LRT says reject for large negative values, then your p-value would be the probability that t is less than minus 1.5, and that would be a one-sided test. Okay, so that's the show for today. I hope you have a wonderful Monday night, and I will see you on Wednesday. Have a great day.